All right, so today I want to talk about, this is kind of maybe it'd be the last postulate that we're going to talk about, and I'm just going to talk about it in brief for the sake of completion. But then after the postulates here, we're going to dive more into quantum field theory, quantum electrodynamics, and all of that stuff that you are here to listen to, because let's be frank, learning the postulates all over again is kind of boring, right? But this is good groundwork that'll make me feel a little bit better on getting into more advanced stuff later. Because really the postulates is some sort of all we really need to be able to get into the more advanced stuff. Because the more advanced stuff, again, is predicated on these guys. Understanding exactly what a state is and going from there, okay? And also, as many of you guys know, the G-2 experiment was released recently, and I want to get into explaining that in some more depth as well. And so after these postulates, we're going to get into that. And that's going to be touching on some quantum electrodynamics. And yeah, so let's just briefly go over to this last postulate here. The wave function for a state, or the wave function or state function for a system, evolves in time according to the time-dependent Schrodinger equation. Okay, so this is sort of what I would call a weak postulate, because in some sense we can kind of derive the Schrodinger equation. We can kind of derive the time-dependent Schrodinger equation, but this is being labeled as a postulate, and so I sort of kind of regard this last postulate as sort of a weak postulate, one that can be derived from other postulates. But nevertheless, this is the starting point for a lot of quantum mechanics. And if we were to break this apart, this guy right here, that's a Hamiltonian. This is an operator, or this is not an operator, this is a number again. This here is the operator, right? This is, we operate on some function with this derivative, and we're going to get some value. We're going to get some eigenvalue that's associated with this operator, multiplied by the wave function again, right? And the one thing here. So if we remember the derivative with respect to time, we already sort of went over this. This is sort of synonymous with the energy, okay, and the derivative with respect to space is sort of synonymous with momentum, right? And we sort of said earlier that the energy is just the time component of the momentum, where the momentum vector, the momentum 4 vector, how do I want to do this? I'll call this sigma. The momentum 4 vector, where sigma goes from 0, 1, 2, 3. This right here sort of is translated into this concept of a 4 vector, where we have P0, P1, P2, and P3. These guys are the spatial components. Again, this is Px, Py, and Pz. And this right here is Pt. This is the time component of our momentum. And this right here is the energy, right? So, and we said that this is synonymous with an operator, right? Right, that we said over here. And then these guys, again, these are synonymous with an operator, dx, or more generally, nabla. This is our spatial operator. All right, so these are the operators, and I can do this in maybe a different color, just highlight operators. These are operators. And this right here is the eigenvalue, and these right here are the eigenvalues for these operators. So again, this is, so we have our time component operator is going to give us sort of the dynamics. So the energy, this is the energy eigenvalue of the time component operator here. But now here's the big but that I want to get into. H in sort of the classical, not classical quantum, but H in the Schrodinger equation is equal to, this is the Hamiltonian, right? This is p squared over 2m plus v of x. This is so this is our kinetic energy. This is our potential energy. So kinetic plus potential energy. Kinetic is usually denoted with a T, and potential is usually denoted with a U. So if we were to actually be more general, we can be more general. Nothing is stopping us from being more general and saying, well, we could have any Hamiltonian. We could have any Hamiltonian, and in which that doesn't necessarily have to take on this form. All we're saying here is that this is a particular Hamiltonian, and it's a function. This is the function of momentum and positions, or momentum, as we know, is mass times the velocity. So it's more of a function of positions. So here's our positions and our derivative of positions. And this looks a little bit more familiar because in many body systems, this is, let's see, Q and Q dot, where Q are sort of these arbitrary coordinates, and we can have n number of them. So we could take like an Atwood machine, for example, in the classical sense. You can define all of its moving parts and all the derivatives of those moving parts, and we get a Hamiltonian. Okay, so the Hamiltonian, again, is for this case in particular, for the Schrodinger case in particular, is the sum. So it's a sum of the potential energy and the kinetic energy, right? But most generally, it is just merely a function of positions and derivatives of positions. But to generalize this even more, we also have this thing called the Lagrangian, right? So the Lagrangian, I'll put a hat, just like the Hamiltonian has a hat on it, is also a function of positions and velocities, like this. So we have this guy right here. This is our Hamiltonian, and this is our Lagrangian. And there's a link between the two. And the link between the two is that the Hamiltonian is equal to the sum of all of the momenta. And I might derive this later, but this is really going over classical field theory. Just the brief rundown on classical field theory minus the Lagrangian on P's and Q's. Q and P's. This is a sum on I. So this is the link between the two. And the Lagrangian and the Hamiltonian, they're merely just functions of positions and their associated momenta. Right, and this is how we find. This is how if we know the Hamiltonian, we could use this equation to calculate the Lagrangian. If we know the Lagrangian, we can use it to calculate the Hamiltonian. Right. So we could say, for example, we could convert to the Schrodinger equation. Well, if this is what the Hamiltonian is equal to, we could theoretically, nothing should be stopping us from doing something like this. Q P times a wave function. And then this guy up here, we have our IH bar and our psi again. The only difference now is that if we're putting this in a quantum context, these guys here have to be states. And let's see, and actually this guy here should be a dot. And I'll put a dot right there. So again, this is going to help us get into quantum chromodynamics because we are Lagrangians inevitably play a role, again, formulating stuff like the standard model and stuff like that. So this is the postulate where that sort of comes into play. Right? I'm not doing any exact calculations yet, but postulate 5 is sort of this postulate that says, okay, if I know a Hamiltonian or a Lagrangian, because I can convert between the two, I should be able to know how the state of a particle changes with time. Okay? And so this is, again, this is the last of the postulates. I'll just add, for sake of completion, that the momentum, I'll actually write this all out here before I leave here. So we have a Lagrangian framework. And if this is stuff that you don't quite know, again, this is quantum field. This is not quantum field. This is sort of a review of classical field theory placed in the context of quantum field theory, so that we begin to organize these concepts a little bit better, so that we could move on forward. Okay. It's a framework. So we have a Lagrangian framework in which the Euler-Lagrange equations play a role. Right, and again, if you don't know what the Euler-Lagrange equations are, I will go over this probably in later lectures. Again, this is just debriefing us on what is to come later. These are the Euler-Lagrange equations, and we can derive everything we know in classical mechanics using just this equation. This is a very, very important equation. Right? I cannot understate, or I cannot overstate how important this is. The Hamiltonian framework looks more like this, where we have the conjugate momenta. The derivative of the conjugate momenta is equal to let's see, pen's starting to bug out a little bit. The derivative with respect to Q of H over Hamiltonian, and Q dot is equal to a derivative with respect to P of H. So this is the Hamiltonian framework. This is the Lagrangian framework. Then we have Noether's theorem that plays an important role. Noether. Noether's theorem. This is another very important concept that shows up in classical field theory. And we have the connection between these two guys, which is right here. I can't remember exactly what the formula is for Noether's theorem off the top of my head. But this is something we will go over this. We will go over this concept later. We will go deeper into this concept later, and we will also go deep into this framework as well. But these are sort of the big topics to take away from this, and to bring it back. This is a Hamiltonian, right? This is the sum. In the Schrodinger case, it's the sum of the kinetic plus the potential energy. But that's just a very specific case of what can be more general, right? We have a function. The Hamiltonian is merely, again, a function of coordinates and derivatives of coordinates. Okay? That's the take-home. The Hamiltonian and the Lagrangian, again, are just functions of these. And like I said, as I've been sort of beating up this example of having a sort of this phase field where you have psi and psi dots, and then at each point we have Lagrangians. I won't draw this out in total again, but we have Lagrangians and we have Hamiltonians at each point. Because, again, they are functions of this and this. So the Lagrangian is going to be different here than it is here. And it's going to be different here than it is here, and different here. They're going to have different values. And we want to find, one of the very, very important things also here is that we want to find what path these states travel, and what's the likelihood of them traveling between states to get to their final state. Or perhaps we have a state that travels like this, or perhaps like this, or perhaps like this. Right, there are all these possible paths, and that's going to be given to us by another very fundamental concept called the action. Right, and the action is the integral of all the possible Lagrangians, again, as a function of q and q dots between two different points, right? So x1 and x2, or actually I'll say between state 1. I don't want to confuse us, between state 1 and state final. So state initial and state final, perhaps. And then over time and space. But yeah, so this action is going to tell us which of these paths are more likely. So this is an action. So this is the action principle. Action principle. So we could see here, the action principle is fundamentally a function of the Lagrangian. The Lagrangian can be transformed into a Hamiltonian, right, by this right here. And then we have Noether's theorem, which fundamentally relies on the Lagrangian, which can then be formulated in terms of the Hamiltonian, and the Hamiltonian shows up right here. And So there's all these connections, all of these connections here between actions, the Noether's theorem of conservation, Lagrangians and Hamiltonians. And so I won't beat this up for too long, and I'll see you guys in the next one.